Today we're tackling something that's super important but often misunderstood: how to properly inspect non-metallic pipes. You see this stuff everywhere, right? But how can you be sure it's actually safe? Well, it turns out there's a whole playbook for this. It's called API 574, and we're going to dive right in.
So let's just start with the most fundamental question of all. With steel, when it corrodes, you can usually see the rust. It's pretty obvious. But with things like composites or plastics, the really dangerous stuff, the kind of defects that cause catastrophic failures, I'm talking about bad bonds or delaminations, they can be completely invisible, just lurking under the surface, waiting to fail without giving you any warning at all.
And look, if you're sitting there thinking, hey, I'll just run a pressure test, that'll catch any problems, I need you to see this. This quote comes straight from the standard, and it is absolutely staggering. It says that joints with up to 85% disbonding have passed a pressure test. Let that sink in for a second. A joint that is literally hanging on by a thread can pass the one test that most people rely on. This right here is why a deeper understanding of inspection is so incredibly critical for safety.
Okay, so where do we even begin with all of this? Well, you have to start right at the beginning. During construction. Getting things right before a pipe even goes into service. That is your first and, frankly, your best line of defense against problems down the road.
Now, during construction, your basic toolkit starts with a simple visual check and, of course, a pressure test. But remember that 85% number we just talked about? That's exactly why those two things alone aren't going to cut it. If you really want to know for sure that a joint is solid, you've got to bring in the heavy hitters. We're talking advanced methods like radiography, which lets you literally see inside the material. And you need specialized tools to confirm a solid bond, something that goes way beyond just tapping it with a coin.
And just look at the level of detail we're talking about here. This isn't just a simple, yep, they're stuck together. No way. For a bell and spigot joint, you have to be asking, is there too much adhesive inside that could end up blocking the flow? For a butt and wrap joint, was the laminate sequence, the actual layers, even done correctly? It's these nitty-gritty details that make all the difference in preventing a failure years later.
So let me just boil it down to the most important point. A pressure test is a leak test. That's it. It is not an integrity test. It's great at telling you if you have a massive hole right now. What it won't tell you about is that hidden weakness, that bad bond that's just waiting to let go under operational stress. Maybe next week, maybe next year.
But this is a total game changer. It's called acoustic emission, or AE, and you actually use it while you're doing the pressure test. The best way to think about it is like putting a set of super sensitive stethoscopes on the pipe. As you slowly ramp up the pressure, the AE system is listening. It can literally hear the tiny pings of fibers breaking or cracks starting to grow, all in real time. This lets you stop the test long before you cause a failure, and it finds weaknesses that would otherwise be completely invisible. Okay, so that covers construction, but what about when the pipe is already up and running in a facility? How do you monitor its health over time? Well, for that, you need a totally different set of tools. API 574 lays out 6 main non-destructive examination, or NDE, techniques just for this. And here's the lineup. You've got ultrasonic testing, radiography, that acoustic emission we just talked about, hardness testing, thermography, and even microwave inspection. Now, the trick is, each of these tools has a very specific job. The real skill is knowing which one to pull out of the bag for the potential problem you're trying to find. So let's break these down a bit, starting with what we call the volumetric methods, the ones that look inside the material. First up is ultrasonic testing, or UT. It's fantastic for finding things like erosion damage. The catch? You need special low-frequency probes, and it's completely blind to something called a kissing bond. That's a scary flaw where two surfaces are touching but aren't actually fused together. Then there's radiography, which is great for seeing internal flaws, but it struggles to identify disbonding clearly. And AE, well, as we saw, it's amazing for catching flaws as they're actively growing, but it doesn't tell you what the flaw is. It just screams, hey, something's happening over here. You'll need another method to pinpoint it. All right, now for the other half of the toolkit. These techniques focus more on the surface and the material properties. A hardness test is pretty straightforward. It can tell you if the resin cured properly in the first place or if it's been damaged over time. Thermography is really cool. It uses an infrared camera to spot temperature differences, which can point to flaws hiding near the surface. And then you have microwave. This is your specialist tool. Remember that kissing bond that UT couldn't see? Microwave can find it. Its only real weakness is that it can't inspect through any kind of metal clotting or coating. Running all of these tests and collecting all this information is really only half the battle.
The next step is arguably the most important one. You have to evaluate the results. Because all the data in the world is completely useless if you can't turn it into a clear diagnosis and, more importantly, a plan of action.
When you strip everything else away, all the tests, all the reports, all the fancy charts, it all comes down to one single goal. There's only one question that truly matters. Is this pipe suitable for continued operation? Can it run safely? Every single evaluation has to lead to a clear answer to that question. And getting to that answer isn't just guesswork. There's a really clear 3-step process you follow. First, you verify. Is the data complete and accurate? Did the inspection actually follow the plan? Second, you identify. You find every single indication, and this part is crucial. You make sure they are sized correctly. And finally, you determine. Based on everything you found, you make the call. Is the pipe fit for service, and if so, for how much longer?
Now, when a situation gets really complex or the damage you find is pretty significant, the good news is you don't have to guess. The industry gives us a powerful engineering toolset called API 579, or Fitness for Service. This allows you to do a really detailed analysis to determine if a component with known flaws could still operate safely under specific conditions.
Okay, so you found a flaw, you've evaluated it, and you've determined it needs attention. So, now what? Well, you've arrived at the action plan phase. This is where you have to decide what you're actually going to do about it.
And as you can see here, there are some very clear triggers for action. If your calculations show that the pipe's remaining life is less than the time until the next scheduled shutdown, you have to act. If the wall thickness drops below the required minimum, you have to act. And if you find a defect during an outage, you have to address it before startup. These are pretty much non-negotiable. Generally, you have two main choices. You can either repair the pipe or re-rate it. A repair is exactly what it sounds like. You physically fix the defect, maybe by replacing a section or filling a pit, to restore the pipe to its original condition. A re-rate is a totally different strategy. You don't actually fix the pipe. Instead, you officially change its operating limits, like lowering the maximum allowable pressure to give yourself a bigger safety margin. And this is an absolutely critical safety interlock. If you decide to re-rate a pipe to a lower pressure, you must, and I mean must, ensure that the system's pressure relief valves are also adjusted to match. If you don't, your safety device is now set for a pipe that no longer exists, and that creates an incredibly dangerous situation. So when you put all of these pieces together, from that initial construction inspection to the on-stream testing, the evaluation, and then the action plan, you start to see that this isn't a one-time event. It's a continuous cycle. If there's one single thing to take away from all of this, it's this simple loop. You test to gather the data, you evaluate that data to understand the condition, you act on your findings, and then you repeat the whole process. That is the absolute foundation of any proactive integrity management system. Which brings us right back to our very first question. We started by asking how you find a catastrophic flaw you can't see. We've just walked through the tools and the methodology to do exactly that. So the final question I have is for you. Now that you have this knowledge, is out of sight, out of mind ever really an excuse?